I'm Sherry Snowbank, and I will be the moderator for this session. Before we get started, I want to remind you that this presentation is being recorded and to type your questions in the chat box on the bottom of your screen. I will wait until the end of the presentation to ask our speaker questions, and we will try to answer as many as we can. It's my pleasure to introduce Madeline Mcgee. Madeline is the monitoring coordinator for the Office of Great Waters at the Wisconsin DNR. Before joining the DNR, she was a postdoctoral researcher at the UW-Madison Center for Limnology. With that, I will turn it over to Madeline.
Hi, everyone. Thank you. Can you guys all see my PowerPoint slides okay?
It is looking good.
Okay, awesome. Thank you everyone for coming to my presentation. Really appreciate it. I realized that one of the other sessions had a much catchier title. So I apologize for my not quite as catchy title, but I appreciate you wanting to be here. So today I'm going to talk about lake-specific climate adaptation strategies or solutions to maintain cold water fish habitat in Wisconsin lakes. Before I get started, I would just like to acknowledge that I right now am in Blue Mounds, Wisconsin, which is outside of Madison on occupied Ho-Chunk lands. And all the lakes that I'm going to be talking about were originally managed and cared for by the indigenous tribes and indigenous people in the land that we now call Wisconsin. And I would like to acknowledge them as the original caretakers of all of our natural resources here in these lands. So with that, I'm gonna jump into my presentation. So I don't have to tell all of you guys, I'm sure, how lakes are really important to us as a state. So they can be a drinking water source for both people and wildlife. They represent, one of Wisconsin's greatest pastimes. Fishing happens, in some of our over 15,000 lakes that we have in the state. Lakes are important home to, non-fish wildlife communities, of course, and are really important to the ecology of our state. And then they're also just really pretty and great to recreate in. I know all of you up in northern Wisconsin get to see and be on many more lakes than I do in a kind of normal day-to-day basis. I'm on a creek and not a lake, but you can't really recreate that feeling that you get on a peaceful lake, either fishing or just kind of taking in the scenery. It's really important part of Wisconsin's culture. And so, lakes are really important to us. And for someone like me, and I'm assuming a lot of you as well, trying to understand how we can effectively manage lakes is really, really important. Because these resources are so valuable to us, we want to make sure that we are caring for them properly and managing them in a way that future generations can get the same or even increased enjoyment from these resources that we do right now. And my specific interest is, how can we manage lakes under climate change? So before I came to the DNR, I did a PhD at UW-Madison and also a postdoc at UW-Madison. And the whole time, my research really focused on understanding how lakes are going to be impacted by climate change, and then what can we do about it? Because to me, it's not really enough to know, what's going to happen. I want to find a way to adapt to it or to prevent negative impacts from happening to our lakes. And so today what I'm going to do is I'm going to use an example of cold water fish habitat adaptation solutions in Wisconsin to illustrate sort of an overarching principle for how we need to approach managing lakes under climate change. And so this general framework is to first identify how lakes will be impacted by climate change, specifically in ways that people care about, but often, other changes are occurring that maybe don't obviously impact kind of what we think we care about, but there actually are impacting, things like fish habitat or ice cover or recreational opportunities. So that's kind of the first step to figuring out, how should we tackle this problem of climate change on our lakes? The second step is really understanding what the mechanisms of impact are. So in order to come up with, solutions, it's not enough to just know what changes are going to happen. It's important to know how those changes are occurring. What is the specific mechanism where you go from, a global or regional climate change to a specific impact in our lake? There's got to be a mechanism or a way that that happens. So identifying that mechanism and understanding that transition of impact from the regional climate down to impacts to our lakes is really important when we're trying to figure out how to adjust our management strategies. And then the third step is, identifying possible adaptation strategies. You can't pick one if you don't have a list of what is available. And then finally, it's picking a specific adaptation strategy or a group of strategies for your particular lake. And I'm sure this is probably obvious to all of you, especially if you heard the last presentation in this session. Every lake is different. They're not all the same. So what works in one lake isn't necessarily going to work in another lake. And it, in fact, could have negative impacts in another lake. So working through this process of understanding the impacts, what the mechanisms of impact are, and then identifying, what is going to work best for your particular lake is what we really need to be doing for a variety of problems or impacts from climate change on our lakes. But to illustrate this process, like I said, I'm going to use an example of cold water fish habitat. So cold water fish habitat, we've got a lot of cold water fish in the state. But the one that I'm going to be focusing on here for this project is Cisco. So Cisco is, these are some pictures of Cisco. It's a small-ish kind of silvery fish. It's native to Wisconsin, native to, not just Wisconsin, all kind of glacial lakes in the Midwest. And Cisco is really important for a couple of reasons to the state. The first is that it is a good native forage base for larger game fish. So some research over the last few years has actually shown that in lakes that have both walleye and Cisco, walleye are larger and they reproduce better in lakes that have Cisco in them, because Cisco are often described as like sticks of butter. They're really good energy sources for fish that prey on them. And Cisco have historically been, a fishery in their own right in the state, both with our tribal communities and in commercial fisheries. So Lake Mendota, which is in southern Wisconsin, but nearer to me, so I just know a little more about it, used to have a multi-million-dollar Cisco fishery in the early part of the 1900s. So this has been a really important fish to kind of the culture and the ecology of Wisconsin. The other reason that I'm looking at Cisco here is that Cisco populations have actually been declining in the recent history. So this graph here on the left is from Cisco assessments, not just in Wisconsin, but actually in Wisconsin, Minnesota, and Michigan. But you can see here with this compilation of data that the mean catch per unit effort, which is essentially a way to estimate the population in lakes, has been decreasing since about the mid-1970s. And so this is really concerning because A, it's a cold water fish, and we kind of expect with climate change that cold water fish will be impacted more quickly than some of the cool or warm water fish, but also because it has been both a commercial and a culturally important fishery across the state, and because it is an important food source for larger game species that are managed across the state. Knowing that these populations have declined is really important and concerning. When we look specifically at Wisconsin, this map shows some work done by Tim Parks at the Wisconsin DNR a few years ago. And all of the dots shown on this map right here are lakes that historically had Cisco present in them. But the red dots show lakes where, when this assessment was done, which was about 2015, when this assessment was done, lakes that still had Cisco in them. And all of the white dots show lakes in Wisconsin where we've lost Cisco populations. And you can see that, there's quite a few down in the southern part of Wisconsin, but there are many lakes in northern Wisconsin that have lost their Cisco populations. And so this is concerning. And we know, like I said, based on other research, that cold water fish populations, be it Cisco or lake trout or some other cold water fish, are likely going to be some of the first impacted by climate change. And when we look further at actual populations in these lakes, so these dots show all the lakes that still have Cisco in them. Even though we do still have a number of lakes with Cisco in them, only a few are actually classified as very high or high populations. Many that do still have Cisco are classified in this low range and also the moderate range. And so that could be an indication that populations are still there, but perhaps they're not high quality, and perhaps these lakes are at risk of losing populations in the future. So before I get into a lot of my research and working through this kind of adaptation strategy approach, I want to provide a little bit more background on this idea of an oxythermal niche and cold water fish habitat. So these plots here, I've got two color graphs. The top plot shows kind of a generic dimictic Wisconsin lake. The top plot is the temperature plot. So you can see these yellowish colors are warmer water temperatures and the bluish colors are cooler water temperatures. As we look from the top to the bottom of the graph, the top of the temperature plot represents the surface of the lake, and the bottom of the plot represents, the bottom waters of the lake. And the plot going from left to right shows the change in temperature through time. So if you were to section this off into kind of one little line, that would essentially be a temperature profile for one day during a typical year. And this shows the temperature profiles as we move from April to December. And you can see the top waters of the lake in the summertime are warmer than the bottom waters. This represents the stratified condition. The spring time and the fall time have pretty consistent temperatures from top to bottom. So these would be the times of year when the lake is well mixed. In the spring and the summer, in the spring and the fall. And not shown here is the ice cover period, where obviously there would be ice cover on the lakes, and the temperature or the lakes might see some reverse stratification under ice cover. The bottom plot here shows dissolved oxygen. So this plot is set up the same way. Looking from the top of the lake is at the top of the graph, the bottom of the lake is at the bottom. And then we move through time from April to December, going from left to right. These blue colors show high levels of dissolved oxygen, and the red colors show lower levels of dissolved oxygen. And I want to take some time to just explain these graphs, because they're gonna come back again a little bit later as I explain some of our results. So these are, like I said, typical kind of conditions for a dimictic lake in Wisconsin. When we're thinking about cold water fish habitat, in the spring period, the whole lake is really good habitat for cold water fish. Water temperatures haven't warmed yet, so it's still pretty cool within the kind of desired thermal ranges, temperature ranges for Cisco and other cold water species. And because the lake is well mixed, there's, pretty high levels of dissolved oxygen from, top to the bottom of the lake. And so fish can, happily swim all around the lake and have lots of habitat. Now, once we start to move into the stratified period, what happens is, the top of the lake is too warm for these fish. These are a cold water fish species, so of course they don't like warm water. But at the same time, the bottom of the lake doesn't have enough dissolved oxygen for them. So what happens when the lake stratifies is this warm water is less dense than the cold water. That's why it stratifies, because of that density gradient with temperature. But what that density gradient does is it prevents oxygen from entering the bottom layers of the water. So the top of the water column where it's warm can be well mixed and it can have lots of oxygen. You can think of, whatever lake you consider your lake that you live on or that you frequent most often. Wave action moving across the lake can input oxygen into that water, and making it available for fish and other wildlife. But what happens during the stratified period is you essentially get this, bar where that temperature changes really quickly, and that bar prevents water from mixing to the lower layers. And so there's no input of oxygen into the bottom of the lake once the lake has set up stratification. So you can think of it, maybe like your bank account, where if you suddenly, lose your job, you're not putting more money into your bank account during that time period. But as I'm sure all of you know, lakes are very productive. And so even a lake that is not, super eutrophic still does have productivity. There's algae, there's, other organic matter that sinks to the bottom of the lake and it starts to decompose. Those decomposition processes use up oxygen. So if we're going to go back to our bank analogy, decomposition is the same as you still having to pay your mortgage or your rent and buy groceries. But at that bottom portion of the lake, there's no oxygen entering in. So we start to build up essentially an oxygen deficit, and we get these anoxic conditions, as you can see in the red. And this situation continues and gets worse, during the summer, where you see in this little cartoon at the bottom that our cisco and other cold water fish are really isolated to a layer kind of in the middle of the lake, a layer where there's still enough dissolved oxygen, but where temperatures are not, too warm for them. And this happens in most of our lakes with cold water fish in Wisconsin. So this is not an unusual condition, as I've described right here. And then in the fall, when lakes start to mix again, the fish have, once again, all kinds of vertical habitat and lots of dissolved oxygen. So they're pretty happy. However, what can happen in, let's say, if we get a really, really warm year where the lake is really warm, or if there is, a very eutrophied lake or lots of runoff from precipitation that can use up the dissolved oxygen, even more dissolved oxygen in the bottom of the lake. What actually happens is we get this situation called oxythermal stress. And in these cases, the whole entire water column is really not suitable for our cold water fish. It's either too warm at the top or it doesn't have enough dissolved oxygen in the areas where temperatures are cool enough. And when this happens, we can get large fish die-off events. Now, this isn't the only reason, of course, for fish die-off events. There are other causes, but this can be one cause of die-off events. And if this happens, maybe once over the whole history of the lake, it's not a huge deal for the populations. Normally, younger fish are a little more tolerant of these types of conditions, so they won't always die during these large die-off events, and they can sustain the population. But if you get these events, multiple years in a row, that can cause basically a localized extinction of cold water fish from your lakes. And we believe that's what's happened to some of the lakes in Wisconsin that have lost cisco in them. And we expect that these changes, or that this type of event is more likely to continue with climate change. And so I'm going to talk about that a little bit next. First, though, I'm going to talk about evidence of this decrease in habitat that we've seen in other lakes. And so this plot shows what we're calling TDO3. I'm not going to go into detail about that. That's just a measure of available habitat. And higher numbers are bad. They indicate more stressful conditions. Lower numbers are good. They indicate less stressful conditions. And so you can see for this particular lake that this habitat metric has decreased. It's increased in number, going from good habitat to bad habitat as we move through time. And what we found through modeling scenarios that I'm going to show here, but also, in literature from other states with cold water fish populations, is that there are two kind of main drivers for this shift from good habitat to bad habitat, both of which can be are influenced by climate change. So this graph here shows the same habitat metric, TDO3, where the load numbers, these purplish and bluish colors are good, and these orangish, yellowish colors are bad. And we can see, like I said, both through modeling simulations, through data analysis in Wisconsin, Michigan, and Minnesota, and also lower portions of Canada, what we find is that as you increase air temperature, you can move a lake or a set of lakes from good habitat to worse habitat. So you start to shift from acceptable to poor habitat with air temperature increases. We also see a shift in good habitat to bad habitat with increases in phosphorus load. Now, increases in phosphorus load can be from changes in land use, but they can also be from climate changes, kind of regardless of any land use changes. So why is this exactly? So back to this type of plot here. On the top, I've overlain the water temperature plot and the dissolved oxygen plot that I showed a few slides ago, just on top of each other for ease. And then these gray areas here represent the normal kind of condition in a typical dimictic lake, where the top portion of the water column is too warm for fish. So I've got it grayed out here to show poor habitat. And the bottom, during a typical year does go, anoxic, or at least to low enough levels, maybe not fully anoxic, but levels that are too low for fish in the bottom portions of the lake. And then we get this kind of narrowing of habitat here right in the middle. Now, if we increase precipitation in your lake watershed, that is very often, most often associated with also an increase in phosphorus loading to the lake. So when we increase phosphorus load to the lake, from a temperature standpoint, that doesn't really make much of a difference, right? The lake is still stratified regardless of how much rain you're getting or how much phosphorus is coming into your lake. So this top grayed out area stays about the same. But when you increase phosphorus loads into your lake because of increased precipitation, what happens is, all of the algae and the plant life in the lake, they take up that nutrient. Phosphorus, it helps them grow. You guys all know this. And so you get these booms in productivity. And when you get booms in productivity, you also get a lot more material, dying after that boom and then sinking to the bottom of the lake where it starts to decompose. And because we have more material decomposing, we actually use up more oxygen in the bottom of the lake, right? Our oxygen bank isn't getting any additional influxes of oxygen during this period, but we're debiting oxygen at a faster rate because we have more material decomposing. So more phosphorus runoff from either increased phosphorus loading in a watershed, increased precipitation, or both decreases fish habitat. So if we know that this is one mechanism of negative climate impact to fish habitat, what might we do about that? Well, some possible actions would be, of course, to reduce phosphorus runoff to the lake. And that's, I would say a typical water quality management strategy anyway. Or possibly add oxygen to the hypolimian, to the bottom waters of the lake. Maybe we can't reduce phosphorus loads for some reason. Maybe there just aren't a lot of, phosphorus coming, there isn't a lot of phosphorus coming into the lake already, so it's hard to reduce it even more. But maybe artificially adding oxygen to the bottom of the lake would help offset this oxygen deficit. Right? So the second change, second climate mechanism that I'm going to talk about is changes in air temperature, and also changes in wind speed. So again, this top plot shows our current condition with poor habitat shaded out with these gray colors. And then this bottom plot shows what could happen during under a climate change scenario. So if we increase air temperature and or either decrease wind speed, what can happen is we cause an earlier stratification to our lake. So just from a temperature standpoint, we are adding a little bit more heat into the lake because of air temperature increases. And when we decrease wind speed, we're setting up stratification earlier in the season because we don't have that mechanical force actually, physically mixing the water during the springtime. There's less of that. So the lake stratifies earlier. So when you get this earlier stratification period, you can see that our grayed out area changes a little bit in depth, not a ton. That is really kind of lake dependent, whether that warm Hypolimian layer will decrease in size, so get shallower, or whether it will increase in size, get deeper into the lake. But regardless of lake specific details, that stratified period does start earlier. So you can see our gray box happens earlier in the year, more towards the beginning of June instead of mid-June. And it also overturns later in the year. In our original case for this lake, it was maybe mid-September when the lake started mixing again, and now it's all the way into October when the lake starts mixing again. So right away, we have this situation where the warm temperatures are in the lake for longer. Okay, because we have this increased stratification duration, regardless of any changes in phosphorus or precipitation in the region, we actually also get an increase in the anoxic conditions in the lake. So this is because as soon as the stratification period starts, that's when the bottom of your lake gets cut off from its oxygen source. So you can imagine in this situation, what's happening is we're not taking that oxygen out more quickly, but what we are doing is we're taking that oxygen out for a longer period of time, right? So if we think about our bank account analogy, it would be the same as, cutting off your income stream for 4 months instead of 3 months. Well, you're going to be in a greater deficit by the end of that 4-month period, right? So that's what's happening here. When we have a longer stratification duration caused by increasing air temperatures, which we have seen in Wisconsin and we expect to continue into the future, and decreasing wind speed, which again, we've seen in Wisconsin over the last 100 years or so, and which we expect to continue into the future, that decreases available habitat. So what could we do about this? Ignoring any climate mitigation efforts, a possible action that we could do would be to somehow reduce stratification duration. And that seems, kind of hard, is kind of hard, but we do have some strategies for doing that I'm going to talk about next. So this is what's happening with our lakes in Wisconsin in relation to cold water fish habitat. And these are the mechanisms of change. So if we think back to our process, we've identified the change, we've identified the mechanisms, we've come up with some possible adaptation actions, but now what we have to do is we have to figure out what's going to work in each of our lakes. So that's the next step that I'm going to talk about. So if we look at our possible adaptation actions, we talked a little bit about aeration. Some of you may be familiar with this, but it's essentially using a tube, a hose with holes in it to pump air into the bottom of the lake. And this is done in some lakes in Wisconsin already. The second was to reduce phosphorus loading. So obviously we can't impact precipitation itself, but we could reduce phosphorus loading in the watershed into the lake. And so if we do this, we'll go to this situation where we move from lots of red, low oxygen conditions to more green, more good, that doesn't make sense, to better conditions, because we're reducing that load, which means we're reducing deoxygenation during decomposition because we have less productivity in our lake. This third idea that I mentioned was artificial destratification. And so this has been done in a few other lakes. So we know that it can be adapted if desired. And so the idea here is you could essentially intentionally mix the lake early in the season and delay the onset of stratification. So what you don't want to do is keep it mixed all year. because that is going to bring more heat to the bottom waters of the lake, which would be bad for cold water fish. But what you can do is if you mix the lake, either through, for example, aerators, having your aerators designed so that they are actually bringing bubbles up to the surface of the lake, that can help cause a longer mixing period in the spring. Or this example here was used on Crystal Lake in northern Wisconsin, actually to try to remove an invasive species, but they used essentially like inflatable trampolines that moved up and down the water column and physically mixed the lake all year round. So the idea here is that if you just mix during the spring, what you can do is you can delay the onset of stratification, like shown here. So this longer white bar is the original kind of stratification onset. And if you artificially mix the lake through these means, you can delay that onset of stratification. So then when you delay the onset of stratification, what you do is you're minimizing the amount of time that your oxygen bank is going to be closed or is not receiving, its oxygen inputs. So then you'll have a smaller kind of net loss of oxygen by the end of the summer. And I really wish I could see you all in person so I could see if that explanation made sense, or if you're all looking at me with confused faces telling me that I don't know what I'm talking about. But these are the kind of three solutions that we've mentioned here. Right, so oxygenate the hypolimian, reduce phosphorus runoff into the lake, and then artificial destratification. What we need to do is figure out what adaptation strategies we should use for any particular lake, because not every solution is going to work for every lake. So right off the bat, for the lakes that I'm going to be talking about, oxygenating the hypolimian was crossed off the list. And the reason for this is that we've seen in other lakes that when you oxygenate the hypolimian, sometimes you can get this area sort of in the middle part of the lake where there still isn't enough dissolved oxygen for fish to survive. And that's shown here in this, this plot here. So the top two plots are temperature. So on the left, it's 1 year, 2014, that didn't have the hypolimian oxygenated. And the second year is when it did have a regular oxygenation of the hypolimian. The bottom two plots show the actual dissolved oxygen levels, with red being low levels. And what you see is that even though there are high levels of oxygen at the bottom of the lake, we get this mid zone where there isn't enough dissolved oxygen, and that can essentially isolate fish down to the deep layers of the lake where maybe they don't have access to their food resources. So the two lakes that I'm going to be talking about, managers and stakeholders kind of decided right away, like, no, we don't think that's a viable option. It's maybe going to be too cumbersome for us to implement, even if we were able to get something up and running. So how do we identify actual optimal actions for our specific lakes? So I'm going to be talking about two lakes in southern Wisconsin, Fish Lake and Lake Mendota. If we look at their historic change in fish habitat, we can see that they both have had a transition from good habitat with these low numbers to poorer habitat with these high numbers. And the degree of change has been roughly similar over the last 35 years or so. But when we actually look at habitat within the lake on a spatial scale, we do see that there's a lot of variability within the lake in what habitat is available to cold water fish. So these lake maps are not to scale. Lake Mendota is like 10 times the size of Fish Lake in surface area, although both lakes have similar depths. They're both about 25-ish meters deep right now. So we can see in August and September, where we usually have the highest degree of stress or the least habitat in our lakes, we can see in Fish Lake that the deep hole is shown in black, these black dots here. We can see that in Fish Lake, we don't really have a lot of habitat. So these colors show that vertical habitat. in a plan view across the lake. And it would make sense that shallower lakes would obviously, or shallow portions of the lake would obviously have less habitat. Deep portions of the lake would probably have more habitat because they're just deeper, there's more vertical habitat. And we see that that's true in Fish Lake, where the most habitat is actually near the deep hole of the lake. However, we see something different in Lake Mendota. What we see in Lake Mendota is that actually there is more habitat, not in the very shallow waters of the lake, but kind of in these mid depths. The deeper areas of the lake actually have less habitat, and these kind of mid depths have more habitat. And we believe that's because Mendota is large enough that there are more upwelling and downwelling events and an internal station in the lake. And so this creates just enough habitat around where there are steep bathymetry changes that what's happening is oxygen is able to go into the colder hypolimnian waters in those areas where it doesn't kind of do the same thing in the deep water of the lake. It's only doing this where there are these steep bathymetry changes and where these are these regular, upwelling and downwelling events that are pulling oxygen into the cooler bottom waters of the lake. So we know that this is what's happening in these two lakes right now. So what if we look at some adaptation strategies? So what we did was we modeled both lakes, Fish Lake and Lake Mendota, under a few different scenarios. So the first scenario shown in black is the historic conditions. So what was the historic habitat from 1976 to 2014 for Lake Mendota, and then 95 to 2014 for Fish Lake. And these black lines show the cumulative distribution function. And on our x-axis, we have our habitat metric, with good being these low numbers on the left and bad habitat being the high numbers on the right. And so this black line just gives us kind of the baseline for what we've historically seen in terms of habitat distribution in the lake. The second scenario we simulated was our climate change scenario. So this is called the A1B scenario. It is the most likely climate change projections for the state of Wisconsin. So we went with that scenario, and that's this red line. And so we can see that in both Fish Lake and Lake Mendota, we are shifting our habitat distribution to poorer habitat under the future climate change scenario. And that is, what we expect to happen: warmer temperatures, more precipitation and runoff into the lakes. And then we looked at two management solutions. So the first management solution is in green. So this takes our climate projection and overlays it with a 50% reduction in phosphorus runoff into the lake. So, this could be done through typical conservation practices, better cropping techniques. This is in southern Wisconsin. So more of an ag landscape than northern Wisconsin, but, reducing phosphorus loads into the lake. And then we can see for Fish Lake, it really didn't make a change. We reduced phosphorus loads by 50%, which is pretty significant. And it was essentially the same as not doing anything. But when we look at Lake Mendota, when we reduced phosphorus loads by 50%, under a climate change projection, we actually created a situation where habitat is better than it is right now. The other management action that we looked at was our climate change projection with this destratification option on top of it. And so what we found for Fish Lake was that using this destratification technique actually shifted our habitat so that it was, about the same, maybe slightly better than our current conditions. But when we use the same management technique for Lake Mendota, what we see is that actually that made things worse. Employing this destratification technique is actually worse than not doing anything. And so this illustrates that, the particular management technique that you use is going to be very dependent on what lake you're looking at. So why did one thing work for one lake and one thing not work for the other lake? So for Fish Lake, go back a little bit. So for Fish Lake is a seepage lake. And, even reducing phosphorus loads to the lake itself didn't make a big impact because there's already a lot of legacy phosphorus built up in the lake itself that gets resuspended, during mixing events, and that gets, released from the sediment during these anoxic conditions. And there's no mechanism right now for removing phosphorus from the lake because there's no outflow. So it just kind of builds up. So that's why reducing that phosphorus load didn't make a big difference. We didn't look at doing something like an alum treatment first, and then reducing the phosphorus loading. And that would be something that maybe could be considered in the future. But looking at Lake Mendota, why did destratifying the lake make things worse? And why did the phosphorus reductions make things a lot better? Well, the phosphorus reductions are pretty straightforward. Lake Mendota is a eutrophic lake. There's already a goal. We picked this 50% because there's already a goal in the watershed to reduce loads to the Aeration chain by 50%. So that's why we're kind of looking at that. And there is an outlet. So loads that are in the lake right now do have a mechanism for moving downstream and exiting the lake. There's also some evidence that there's less internal loading during the year because of different sediment chemistries in Lake Mendota compared to Fish Lake. But this destratification thing, why did it work in Fish Lake but didn't work in Lake Mendota? So if we looked only at the dissolved oxygen, we would say that this destratification technique did work. It actually lowered that oxygen deficit, as you can see in this figure right here, compared to kind of normal conditions. We have, we're only in this anoxic condition in the lower 5 meters or so of the water column compared to the lower 10 to 12 meters. That is under kind of a normal situation right now. But what happened was Lake Mendota right now, with a climate change, projection on top of it, is kind of at a little bit of a tipping point where it's dimictic right now, but if things change, let's say we get an increase in wind speed instead of a decrease in wind speed, the surface area is large enough that we could actually switch the lake from a dimictic lake to maybe a polymictic lake or a monomictic lake, assuming it's still ice covered in the wintertime. And so you can see that that's actually what happened in our scenario that we ran. When we mixed the lake artificially in the spring, we delayed the onset of stratification just enough that enough heat was able to enter the full water column from the top to the bottom, that even though we stopped our destratification, destratification processes in June, there had been enough heat added that it allowed the lake to remain mixed. And because the lake remained mixed through the duration of the summer, those bottom temperatures of the lake were too warm for our Cisco and other cold water fish. That's kind of what happened there. So the take homes are, in small isolated lakes, loading reductions may not improve habitat in the lakes. And so this is really important to understand because that's often kind of our first attempt at preserving cold water fish habitat is, well, increase water quality, reduce phosphorus loads to the lake. But that may not work for many of these lakes. And in large lakes, artificial destratification does not improve habitat, and it in fact makes habitat worse. So this is an example of what works for one lake does not work for another lake, and you can't just always pick and choose what should be done for any lake. What you need to do is you need to be thoughtful about the mechanisms and the impacts so that we don't have kind of unintended negative consequences when we're trying to manage our lakes. So next steps for this work, working with some folks at UW-Madison to expand this work to lakes, cold water lakes across Wisconsin, and add a few more variables of interest. So we know in northern Wisconsin lakes, there has been increase in DOC or lake browning. You may have heard in some lakes, and that can impact how heat is put into the lake, or how heat is distributed in the lake, and it can impact cold water fish habitat. We already know phosphorus load makes a difference, but there are also differences in morphometry, so lake depth, lake surface area, latitude. So what exactly is the climate change expected at that location, and what are the current lake conditions? So the two lakes that we've looked at that I showed here are in southern Wisconsin, which has a very different climate than northern Wisconsin. So we expect there to be some latitudinal differences on what may or may not work. And then using this information, what we hope to do is essentially help come up with a management map and some management options where lake managers or folks are interested could look at their particular lake, figure out what are the characteristics of that lake, and then figure out whether your lake will be resilient to climate changes. By resilient, we mean that cold water fish habitat will be maintained in the lake. Obviously, there can be other climate change impacts. They may not be resilient to everything. Where maybe there are lakes where nothing can be done. Maybe there aren't any feasible management strategies, and we can expect that there will be some localized extinction of cold water fish in those lakes. Or lakes where maybe phosphorus reduction or land cover changes or an engineered solution like artificial stratification or hypoliminetic oxygenation might be appropriate. And don't try to find your lake on this map. This is just for an illustrative purpose. This is not what we think the lake distributions are going to be like with these scenarios. We're just trying to illustrate what we hope to accomplish with this work. So with that, I would like to thank some funding sources and organizations that have helped pull together all of this research, and open it up for questions.
Thank you, Madeline. That was very interesting. Again, if you'd like to ask a question, please use the chat feature, bottom of your screen in the middle.
Yeah, so Pat had a question. Patrick, don't know what you prefer, had a question about fish regulations as another factor that can affect management action to support cold water species resiliency. For example, less fish kept by fishing people. Yes and no. In terms of habitat, just what habitat is available itself. Managing something like the fishery itself probably isn't going to impact habitat, but and I say this as not an actual fisheries manager, but managing for maybe some of those lakes that are going to be kind of on the bubble can be a viable management solution in keeping the populations themselves in those lakes, if that makes sense. So if you think about, when I talked about in the beginning about how fish during these die-off events, the younger fish species are usually a little more resilient. Usually in these fish die-off events, you're not killing every single fish in the lake. So it stands to reason that the more fish you have in the lake, while you may have more fish die, you'll have more fish left over to sustain the population. So that can be an effective management option from the population standpoint, just not from the habitat specific standpoint, if that makes sense. By the same reasoning, things like increasing spawning habitat in some of these lakes, or managing predation in some of these lakes would have the same effect. You're not necessarily improving the available habitat itself, but you are improving the health of the population, which would make it more resilient to times of decreased habitat, if that makes sense.
Any other questions for Madeline? Oh, there we go. Are you familiar with the Midwest Glacial Lakes Partnership Conservation Planning Tool that shares data on these fisheries in the Midwest?
Yes, I am. And for those of you who are not, I highly recommend if you're interested in this topic to, you can just Google, can't talk, Google Midwest Glacial Lakes Partnership, and their conservation planning tool will come up. And so they do have assessments of which lakes may be vulnerable to climate change impacts for different types of fish populations. And different watershed kind of threat indices and planning metrics, risk metrics that can be very useful from a planning standpoint. If you are interested in climate change, climate adaptation, or climate impacts, the Wisconsin Initiative on Climate Change Impacts, which I am a member of, is right now putting together a second assessment report. It is supposed to be coming out in the fall, so September, October timeframe. And I would encourage you to keep your eye out for information on that when it's available. The fisheries work group the last time really focused a lot on streams, on cold water streams, but for this next assessment report, they're expanding their work into more lake work. The Water Resources Working Group also is talking about some additional, lake fish impacts, as well as possible adaptation strategies. And those adaptation strategies would obviously be more inclusive than just fish habitat. They would cover other climate change impacts to lakes. So I would encourage you to keep an eye out for that coming in September or October.
All right. I am not seeing any other questions, so I would like to thank you again, Madeline. Please use your reaction buttons on the bottom of your screen for applaud or a thumbs up to show your appreciation for our presenter. And I'd also like to thank all our sponsors for their